Hey everyone, in this chapter we are going to further our exploration of this concept of energy. Taking a look at this picture, we can see that the roller coaster must have some kinetic energy due to motion to make it up through that loop, but does it contain any other types of energy? And that's what we want to focus on in here. From last chapter we found out that work done transfers energy into objects. Specifically, it's kinetic energy, that energy of motion. As we talked about the flip side of that definition, that if an object has energy, then it has the ability to do work. Kinetic energy is the energy of motion, while potential energy, which will be labeled U here, has the potential to do work. It's energy associated with a position or a location in the system here. Going back to our money analogy, let's think of kinetic energy as cash, energy, money that can move around very quickly. We can think of potential energy as a savings account, something that you can store up and use for another time, but you don't necessarily have to use at that moment. In a savings account, you have the potential to buy something, but you don't have to at that moment. We want to try a few examples here of this idea of potential energy. We look at energy due to its different arrangements. First, we're going to look at lifting a book. As the book is lifted, I push upwards on the book while the force of gravity is pushing downwards. The book is going through a displacement. That displacement is in the upwards direction, and that means I have done positive work. Energy has left me and gone into the book, while gravity did negative work during that same displacement. Now, if we focus on the beginning and end points of the demonstration, there was no kinetic energy at the beginning, and there was no kinetic energy at the end. So if you look at my change in kinetic energy, my change in kinetic energy is 0. And if there is no change in kinetic energy, then the net work must be 0 as well. But I know I did positive work, and I know that gravity did negative work. So if you look at it, as I lifted up, energy had left my body and went into the book. But since it didn't turn into kinetic energy, it had to turn into something else, and it turned into energy that was stored in Earth's gravitational field. The book now has a greater potential to do work now that it's lifted off the ground. So let's look at the next scenario. If the book is dropped from this height, the gravitational potential energy does not remain in the book. The book does not want to hold on and store all that energy. So gravity does positive work and pulls it to the ground, and since gravity is the only force acting on it, kinetic energy increases as it reaches the ground. And in this demonstration, potential energy is now turning into kinetic energy by the time it reaches the floor. So the book had energy. It has the potential to do work. And watch what happens when that book finally hits a can. When the book reaches the can, its energy allows the book to push downwards on the can, and the can is also displaced downwards. That means positive work was done on the book, causing that can to be crushed. This is another way that accident investigators know how fast someone's going when they hit a guardrail. So if you look at that picture of the guardrail, they know how far the guardrail has been displaced. They know the amount of force that it would take to warp the guardrail, that amount, and then that allows them to calculate the work done on the guardrail by the car. And this work done has to equal the change in kinetic energy, or the kinetic energy the car had before it ran into the guardrail, assuming that all the kinetic energy was transferred into work and moving the guardrail. No heat, sound, any other wasteful forms of energy happened. So now let's look at a spring. The spring is unstressed and no work has been done yet. When I pull or push the spring in a certain direction, I do positive work on the spring, and the spring has done negative work. If we look at the kinetic energy before and after, the kinetic energy before the spring was stretched was 0, and after was still 0. And again, I know work was done, so where did that energy go? It's now stored in the stretch of the spring, in the elastic potential energy. That energy has changed and is stored in the spring and does not want to remain in the spring. The spring wants to collapse. It has the potential to collapse and turn into moving energy again. So when we talk about the forces involved with energy, we can categorize them into two types. And the two types that we have here are conservative and non-conservative forces. With conservative forces, the only thing we care about is where it started and where it ended. A conservative force does work that is path independent. We only care about two locations. And when you look at those locations, we see that the network around the closed path is zero. So examples of this would be gravity or springs. Those types of forces only care about where the object started and where the object ended. They don't care about the path that it takes to get there. On the other side, non-conservative forces are path dependent, means that the entire trip you take does matter. And when you look at the work done over that entire trip, it will not add up to zero. And if that's the case, examples that we have are our applied forces or frictional forces. We've shown before that if I push a box one way, friction does negative work against it. If I push the box back to its original location, friction also does negative work on that trip as well. So it's constantly taking energy out of the system. And an applied force can do the same thing. It can add energy to the system or take away energy from the system. For a conservative force, you can see that path A or B does not matter how you get from one point to the other. All it's going to care about is starts and finishes. So if we want to look at the work done around this closed path here, we know that work is the integral of force dotted with displacement. So if we write in our force equation for path 1, the work done along path 1 is 4x in the I direction, dotted with dl, also in the I direction. We get positive work done for this path. If I do that for path 2, during path 2, the force is to the right again, and now the displacement is straight up. Those make 90-degree angles with each other, so no work is done here. If I look at the top path, this is in the negative I direction for our displacement. So 4x in the negative I direction now gives us negative work done over path 3. And finally, for path 4, we see our force is still to the right and the object is moving downwards. Again, 90 degrees apart gives us no work done. So if you go around that path and you add up the positive work, the negative work, and the zero work done on each location, you can find out that the total work here done is 0. So that means whatever this force is a conservative force. Not caring about the path that it travels, and the total work done around the path adds up to being 0. And work can then be defined as the change in potential energy. So work would be the integral of force dotted with displacement, force dot dr, and what that will equal is a negative change in potential energy. So like we talked about, if the work is done by a conservative force, like gravity, what it's going to try to do is decrease the potential energy of the object at any point. That's why it's a negative change in potential. So if I want to look for just the change in potential energy there, the change in potential energy there is the negative force dotted with displacement. So we'd have to integrate both sides if we'd want to find how the energy changes with a force over a distance. If I wanted to solve for force, I can just rearrange that and solve for force to be the negative derivative of energy with respect to distance. So there's a couple ways you can solve for these things, and we're going to explore that further in this class and in this section.